Hi, Peter. I can see you on the screen. Good to see you.
To see you. Where are you sitting? You're not looking like in an office. I see a kitchen.
No, this is our new office. We are in
No
the
kidding.
kitchen. Yeah, come and see us. We're in Guildford with a lovely office, and this is well, we're not quite finished fitting it out, so but we're there, and it's looking good. Hazel's just bought some beautiful flowers that are behind us.
Looking good.
Yeah. Great. We've just got our alarm to signal that we're kicking off. I think we've got pretty much most people joined. Thank you for joining our CPD on minimising overheating risk in buildings. As I just mentioned to Peter, who's on our screen, we are speaking from the kitchen of our new offices in Guildford. I'm Anna. I'm one of the co-founders of SRE and the managing director.
I'm Meera Devi, one of the building physics consultants specializing in overheating assessments and other building regulations.
And I'm Alicia. I'm also a building physics consultant specializing in environmental modeling and compliance modeling.
We've been overwhelmed by the response we've had to our current series of CPDs. We're aware that there are quite a large number of you on today, and you're going to have different requirements in terms of the amount of technical detail that you want to get out of today. So we've tried to strike a middle ground. I'm sitting next to two highly technical experts here, and they wanted to include quite a lot of technical detail, but we are going to be releasing a briefing note in a couple of weeks. Hazel's going to send it out, which will be packed of all things technical. So I know many of you will be happy with that. One of the many changes that we've seen in the 19 years that we've been doing what we're doing is an increasing risk of overheating in buildings. Obviously, the causal factor that springs to mind is climate change and the associated extremely high temperatures in summer, but there are various other causal factors which we're going to touch on later. Overheating in buildings has obvious impacts on health and well-being, and there's been, it's very well documented, and also there are increasingly a large number of heat-related deaths each year. Even without the relatively recent introduction of Part O into building regulations for the reasons above, and to future-proof our buildings against existing temperature rises, we do need to ensure that we are building buildings with minimal risk to overheating. Alicia, Meera and I are going to be talking for about 25 minutes, and then we'll be leaving room for questions. We will be finishing quite promptly at 1:45. We're going to start sharing our screen now. We're sharing our screen. Meera's going to start talking today by giving a bit of an overview of what we mean when we talk about, can we get the next slide? She's going to give a bit of an overview about what we mean when we talk about overheating. Understanding the causes and effects of overheating is going to put the context for when we go in to talk much more broadly about the passive and active measures that can be put in place to minimise risk. We're aware that probably all of you will be involved in projects that are beyond the early stages of design, and also many of you will be working on retrofit projects. So we've tried to include an entire section that's looking at later stage designs, solutions, again, minimising heating risk. And I'm sure you're all aware that it's Part O that has been brought in to legislate in this area. However, there are other standards where overheating needs to be taken into account. I do need to say that we've actually had a fire alarm today, and we've been outside for quite a bit of the morning. So this presentation isn't going to be quite as slick as we would have wanted to, but we have been practicing for a while. Meera, you're going to start with the definition.
Thanks, Anna. The term overheating refers to the discomfort the occupants caused by accumulation of warmth within a building. The World Health Organization guidance on thermal comfort states that in temperate zones, temperatures above 24 degrees Celsius can cause discomfort to the more fragile and susceptible members of the population. It is important to note that although air temperature is used to assess overheating, There are other environmental factors associated with overheating that affects the actual temperature as it is perceived by humans. These other environmental factors include lack of air movement, relative humidity, radiant heat, and period of exposure. Recently, human-induced climate change has had observable effects on the environment. As the graph shows, the global temperatures are rising, and as we all know, the global average temperatures have risen more than 1 degree Celsius than the average temperatures of 19th century. Experts believe that if the global average temperature is not limited to well below 2 degrees Celsius than the pre-industrial levels, we will have to face serious consequences of climate change. As the temperatures increases, our cities warm up, creating a phenomenon known as urban heat island effect. As part of the UK's drive to achieving net zero emissions by 2050, we are trying to reduce the energy demands of the building. For that, we are constructing highly insulated buildings with increased air tightness and low ventilation rates, which causes the heat to trap inside. Building orientation plays another key role. For example, if a building has its larger sides exposed to east and west, it has high risk of overheating. This is because the solar gains are maximum from these orientations, and moreover, it's difficult to shade these sides. Most modern buildings today have high glazed areas, and this is another causal factor for overheating. Low thermal mass becomes another reason for overheating. For example, most of the prefabricated structures that we use today have very low thermal mass. Prefabricated structures can be great in terms of quality, time, cost, and waste effectiveness. However, lack of thermal mass can lead to overheating. Internal gains from various activities, people, equipments, appliances can all build up within a space. And if this built-up heat is not expelled from the building by natural or mechanical ventilation, it can lead to overheating. Sometimes there may be restrictions on opening windows due to noise, pollution, or security concerns. Poor management of inadequate services, poorly insulated pipeworks in risers and voids can all increase the risk of overheating in a building. Alicia will now explain why overheating becomes a concern.
As Anna had mentioned, excessive heat can reduce the productivity and induce stress in people. Hot spaces can also cause heat-related issues in both elderly and young children. Overheating can cause sleep disruptions, which can lead to many other health issues. As shown on the graph, it is estimated that, on an average, there are around 2,000 heat-related deaths, both in England and Wales, each year. And with the temperature rising, it is estimated to more than triple by the middle of the century. The UK Climate Projections 2018 predicts that there would be a 2-degree global warming above the 1981 to 2000 baseline by 2050 and a 4-degree global warming by 2080. However, although they are predicting a 4-degree global warming across the globe, this warming is not going to be uniform. The UKCP predicts that if you look at the south end of England, it is going to overheat by around 8 degrees Celsius by 2018, whereas the global average temperature rise will only be a 4 degrees Celsius.
There are a number of mitigation measures to reduce the risk of overheating. Ideally, passive measures will be considered in the early design stage in order to minimise the use of active measures. This is actually Hoof House's show house. We've been working with Hoof House since 2007. I know that we've got Peter Hoof on this presentation, which is great. And they use passive measures quite extensively in the design and orientation of their buildings to good effect. Building orientation needs to balance the need for solar gains in winter with the need for protection from the summer sun. Buildings should ideally be orientated with the largest facade facing south, ideally within 30 degrees plus or minus. Although changing a building's orientation isn't going to be viable for those of you who are doing retrofitting projects, adding external shading is. Horizontal shading is recommended for south-facing facades. Overhangs and external shading. It's advised to subtend with an angle of 60 degrees from the lowest level of glazing in order to ensure the building can benefit from the lower sun in the winter for solar gains and protect against the higher summer sun. On the east and west facing facades, vertical shading is recommended, and the use of vertical fins or louvered shutters are examples of good vertical shading there. Vegetation, although vegetation isn't taken into account for compliance with Part O, it does obviously have ecology and biodiversity benefits, and it can also be really useful for providing external shading. Deciduous trees, which are trees which shed their leaves in winter, enable a building to benefit from the winter sun in order to have a positive solar gain in winter, but also to protect it again in the summer to prevent overheating. Solar reflective surfaces are a relatively recent technology. And what better way to minimise solar gain than through reflecting the sun's rays? Examples would include solar films, reflective paints, and cool roofs. Again, it's a relatively new technology, and there are some issues with potential glint and glare, but that's something that we do look into with our studies. But it is very useful for retrofit projects where other factors are more limited. We all know that glazing is very key for visual and thermal comfort in any building. And as Alicia has touched on, a lot of modern buildings do have a lot of glazing. However, there are important factors to consider in order to minimise overheating. Firstly, it's important to have the correct window to wall ratio. Leading research organisations such as LETI and Passive House Trust publish guidance according to the building use. For example, they recommend 20 to 25% window to wall ratio for south-facing facades, and 10 to 15% window to wall ratio for east and west facing facades for residential buildings. However, as we all know, each building is unique and each context is unique. So we also do glazing optimization studies to ensure that the glazing for your building is designed to kind of maximize all benefits. Secondly, when choosing glazing, it's important to choose the correct glazing. And this is where we need to be thinking about U values and G values. U values measure the rate of thermal transmittance through any structure or any building fabric. And it's really important to get the lowest U value that you can possibly get for your glazing in order to reduce heat loss in the winter. G values measure solar transmittance, and it's really important that the correct G value is chosen for your product your building in order to reduce overheating in summer, but also to balance the need for social gain in winter, solar gain. We would always recommend triple glazing. However, where that's not possible, we do recommend double glazing with the lowest possible U and G values. Mira's now going to talk about other design factors that need to be taken into account.
So when it comes to the building form, a simple design is always preferred. The aim is to reduce the area of the exposed surfaces and obtain an optimal surface area to volume ratio. Simple design can also be great in terms of reducing the embodied carbon of the building. As we all know, the hot air tends to rise above, and with higher ceilings, this hot air can accumulate on the top of the room, allowing the lower portion of the room to remain at a cooler temperature. And moreover, higher ceilings can foster airflow within a space and thus help in reducing the temperatures of the spaces. Thermal mass is the material's capacity to absorb, store, and release heat. Thermal mass can be used to absorb heat during the day, preventing overheating of the spaces. And at night, when it is cooler outside, the heat can be released back into the space. Timber and steel frame structures are classified as lightweight and hence have low thermal mass, whereas the high thermal mass structures would be brick, concrete, or stone. When considering thermal mass, it is important to consider the thermal lag of the material. Thermal lag is the rate at which a material absorbs, stores, and releases heat. When the material with correct thermal lag is applied to your building, thermal mass can be used to keep your building cool in summer. However, if the material with correct thermal lag is not applied to your building, it can cause discomfort and also increase your energy use. For example, if thermal mass is not correctly applied, sometimes it can absorb all the heat that you produce in winter and radiate it back to you in summer when it is not desired. Moreover, reducing the embodied carbon of a building is something that we are all concerned today, and some of these high thermal mass materials can have high embodied energy. So we need to be really careful when we are considering. What we need to be doing is find the right material with right thermal lag and right thermal mass for your building with the help of dynamic simulations and whole life carbon assessments and achieve a perfect balance between both. Phase change materials of PCMs are innovative materials that add thermal mass to a lightweight structure. It comes in the form of a plasterboard, and a board as thick as a plasterboard can give thermal mass similar to that of 100 mm concrete, which is really great. So there is a growing interest for this material in the market as it can be used as a lightweight substitute for other high mass structures. And the way it works is these plasterboards have got tiny microscopic glass particles filled with paraffin wax. During the day, when the temperature of the room reaches a certain limit, this wax melts inside, changing its phase from solid to liquid. And the energy for this phase change is taken from within the room, allowing the room to be at a cooler temperature. And at night, when the room cools down, this glass particles or the paraffin wax change its state back to the solid, releasing heat back into the room. So what is important is we need to have the windows of the rooms open at night in order to expel the heat from the building and allow the board to cool. Recently, in one of the projects that we worked with D-Rose Planning in central London, where it was difficult to comply with Part O, we recommended phase change materials and found that the results drastically improved. Nighttime ventilation or night purging is the next crucial factor. We have been talking about thermal mass and phase change materials, and all of these materials radiate heat back into the room at night. And so having proper nighttime ventilation is really important. So all the architects listening, you need to have provisions in your building for safe nighttime ventilation, similar to what you see in this image. So when we are considering thermal mass and phase change materials, nighttime ventilation should go hand in hand. Alicia will now explain about the other ventilation aspects.
We've got such an eco fit out that our lights go out if we're not moving. So Hazel's just moving to put them back on. Alicia.
Thank you, Meera. So ventilation plays a key role in maintaining the thermal comfort and the quality of air within spaces. So what better way to ventilate a space? The first and the obvious answer, openable windows. Whenever there are no restrictions placed on opening windows due to noise, pollution, or security reasons, we should always opt for openable windows as much as possible. And also the right placement of windows is very important. Although we can achieve cross ventilation by adding openings on opposite facades of a dwelling or on the adjacent facades of the dwelling, the approved document Part O defines cross ventilation as the ability to ventilate a space using openings on the opposite facades of a dwelling and not by-way openings on the adjacent facade. Hence, corner flats pose issues with cross ventilation. The next one would be stack ventilation. Stack ventilation is a commonly used technique where it uses the principle that with air pressure differences due to height, the air is pulled from the spaces and released outside. The temperature difference moves the air, and the hot air, which is of lower pressure, rises up and is replaced by the colder air, which is from outside. To attain the best possible formula, stack ventilation is always combined with Bernoulli's principle. Bernoulli's principle is a simple principle of fluid dynamics. The faster the air moves, the lower its pressure. For example, the air which is farthest from the ground surface has lesser obstruction, and so it moves faster compared to the air which is closer to the ground surface, which is less obstructed. So in order for the Bernoulli's principle to work effectively, it requires a higher airspeed, while stack ventilation can work even on a still breezeless days. Now, Anna will explain, sorry, my mistake.
Air tunnels,
Yes.
the exciting bit.
Wind catchers, like the name suggests, captures the wind using compartmentalized towers and circulate it within the spaces. The hot air is then released through one of the compartments in the tower and using the principle of stack ventilation. It has to be noted that at no point there is no interaction between hot air and the cold air. The next passive measure is earth air tunnels. It uses the simple principle that at reasonable depths below the ground surface, the temperature of the ground is almost similar to the average mean air temperature of that location. Hence, the earth air tunnels utilizes pipes or a network of pipes which are buried deep into the ground to absorb heat or release heat into the surface. For example, on summer days, you can pass the hot air into the pipes, which can then be cooled down by the ground temperature and reintroduced into the spaces. Similarly, on winter days, the cold air is passed through the pipes, warmed up by the ground temperature, and then introduced into the space. Now, Anna can explain more about ways to minimize heat gains within spaces.
Thank you, Alicia. I think it's worth noting that when we did our kind of dress rehearsal that we did with the team, we had some really interesting questions and discussions around that slide that Alicia's just been talking about. And if any of you have questions, then do put the questions in the chat because we will have time after, and Hazel's compiling questions, but there'll also be opportunities to ask questions over the mic as well. So definitely store them up. Thank you for that, Alicia. Although these measures that I'm just going to cover briefly don't help with compliance with Part O because it doesn't take them into consideration, because Part O actually has predefined profiles for internal gains. The minimising internal heat gains does help with compliance with other standards that we're going to talk about later. No matter what a space is used for, there is always going to be some form of internal gains generated either from the activities of the building user, such as cooking, drying clothes, but also through fixtures like lighting. To minimise them, using as higher performing lighting and appliances as possible is going to help. We have worked on a lot of buildings, especially multi-residential buildings, where enclosed areas are very difficult to get away from. Student accommodations, having a student myself, student accommodation blocks are renowned for quite hot internal enclosed corridors, for example. We've worked on a lot of projects in Brighton, where we've learned from very early on, we need to be looking at the design of these buildings to ensure as many passive measures can be included in the design in order to minimise these internal heat gains. One of the reasons, obviously, for these as well is because communal pipe work often runs through these corridors. And even though Part O doesn't consider these kind of enclosed areas for the modelling, it does include the modelling for adjacent areas. So we need to be really careful about ventilating these enclosed areas. And again, early stage conversations are really important. Mira Davies now going to look at more of the active measures that need to be considered for minimising overheating risk.
As Anna explained, we always try to recommend passive measures, but sometimes active measures are inevitable. So we discuss some of them. MVHR stands for Mechanical Ventilation with Heat Recovery. It is a whole house ventilation system that supplies and extracts air from the property. This system can reduce the heating and cooling demands of your building, and if correctly installed, can make your home more energy efficient. It should be noted that for the MVHR systems to work efficiently, you need to have a good air tightness level for the building. And we recommend MVHR in situations where natural ventilation alone cannot solve the overheating issue. And also there are restrictions in opening windows due to noise, pollution, or security. Purge ventilation is a manually controlled ventilation of a space or a room at a relatively high rate to rapidly dilute the pollutants or water vapor. It can be done by active measures, by the use of fans or extract, and by natural measures, example, by opening the windows. Adding ceiling fans to the space can greatly reduce the overheating. Although it doesn't reduce the air temperature, it can, however, mitigate the effects of overheating on building users. And whenever there is a communal system present in the building, we generally give recommendations on how to reduce the heat gains from these systems. And so the architects can coordinate with the mechanical engineers to ensure that these recommendations are followed. And some of the recommendations include adding insulation to pipeworks, heat interface units and storage vessels, lowering the flow temperatures in the communal pipework and systems, having energy efficient systems and control strategies, and minimizing pipe runs. Alicia will now cover other design recommendations and solutions that can be considered at a later stages of the design.
Thank you, Mira. It is best practice to always involve a sustainability consultant as early as possible so they can make the appropriate recommendations. Unfortunately, this is not the case, and it leaves them constrained to very minimal design solutions, which often interferes with the frozen design. However, we are recommending certain solutions and recommendations that can be noted when we are too far ahead in the design stage. We had already mentioned that not all windows can be opened due to restrictions posed by noise, pollution, or security reasons. But wherever feasible, we have to opt for openable windows and reduced fixed glazing. The approved document Part O puts restriction on opening ground floor bedroom windows at night due to security reasons. In such situations, we can opt for tilt and turn windows, which can open as side hung during day and as bottom hung during night, providing a secure nighttime ventilation. In addition, we can also incorporate security grills or internal lockable levered shutters. In one of our recent projects in central London for Savills, we were advising on the thermal comfort, and the building was not able to comply with the Part O regulations. There, we recommended internal lockable levered shutters, which helped with the nighttime ventilation and allowed the building to meet the Part O requirements. Another measure would be to split the window, to opt for a small clear-story window at the top, which can be opened at night securely to provide nighttime ventilation. Acoustically attenuated vents, like shown in the image, it can be incorporated to provide a continuous ventilation rate within the spaces. The architects always love full-height vertical windows, but we should always opt for horizontal windows and preferably side-hung so that it provides a larger openable area. The G value should be as low as possible, but it has a bad impact on the SAP. So we have to always look into a workable value which can help support the SAP as well as the overheating assessment. When the previous recommendations are not feasible or good enough to bring your building to pass the Part 2 overheating assessment, you can look at ways to incorporate thermal mass into the structure. So the first and the easiest fix would be to add phase change materials, as it can easily replace the plaster boards from the walls and ceiling and add that extra thermal mass. But it has to be noted that phase change materials are relatively expensive, and so it is not feasible for majority of the projects. In such situations, you can always replace the lightweight internal partitions with blockwork. In one of our recent projects in Hounslow, which was a council home, we had recommended swapping the internal lightweight partitions with blockwork, which has significantly improved the thermal mass and helped the building achieve the required credits for Part 2. Similarly, exposed concrete or exposed surface can also significantly improve the thermal mass of the structure.
Now we move on to regulation standards and methodologies. Part 2 became mandatory for residential buildings in the UK in June 2022. And the buildings that need to comply with Part 2 include residences, flats, student accommodations, care homes, and student accommodation for children below 5 years of age. Often clients have asked us questions as to why student accommodation and care homes are assessed under Part 2, whereas hotels are not. And this has to do with the period of occupancy. Hotels have a shorter period of occupancy, whereas for student accommodation and care homes, they have a prolonged occupancy. And there are two ways to achieve Part 2 regulations. It's simplified method and dynamic simulation method. In simplified method, your building needs to satisfy certain criteria regarding location, external shading, maximum glazing area, G value of the glazing, minimum free area, and of course, cross ventilation. Whereas the dynamic simulation route follows TM59 methodologies. However, it has got certain additional conditions than the TM59 methodology. Over a period of time, our clients have contacted us with several questions regarding Part 2, and so we are going to cover some of the frequently asked questions here. Part 2 or TM59 has some additional criteria for bedrooms and for the nighttime temperatures of the bedrooms, and so the bedrooms will have to meet both daytime and nighttime criteria. And as Alicia explained earlier, as per Part 2, the ground floor bedroom windows cannot be opened at night unless there is secure measures to open them. The windows at unoccupied rooms cannot be opened at night. We cannot also consider the shading from internal blinds or internal lockable shutters. We also cannot consider the shading from vegetation. This is because the Part 2 requires the building itself to be performing well without other contributing factors, and hence considers a worst case scenario. Part 2 has got predefined profiles for opening windows and internal gains, which cannot be altered. In addition to that, Part 2 requires the building to be assessed with future weather scenario. It is not mandatory to achieve a pass with the future weather scenario. However, the results have to be documented and future recommendations will also have to be provided. Often clients do ask us questions because if the building does not comply with the future building weather files, can we delete this section from the report? However, we'd like to take this opportunity to clarify that we are not able to do it. It's because it is mandatory that the section should be included in the report and the recommendation need to be provided. And I will now explain about other standards and methodologies.
I'm realizing we're eating into our time for questions. So just briefly, although Part 2 is the only regulation that applies specifically to overheating, we've got on the screen a list of others where overheating does need to be taken into account. These standards include TM52, which is a CPD guidance, BB, which stands for Building Bulletin 101, which is school guidance published by the government, which applies specifically for schools, and HTM, which is published by the NHS for healthcare buildings. The London plan recommends the cooling hierarchy, and that's something that we've been talking a bit indirectly today. Obviously, they do ask for consideration to be placed on passive measures before even looking at active measures. And complying with all these above standards is also necessary to achieve certain credits for BREEAM, LEED and WELL. We've now got just about 10 minutes for questions. I know that there are some, so please put them in the chat or unmic yourselves and ask the questions.
We haven't had any in the chat.
I like to learn more about the change phasing material.
Peter, good to see you. Thank you. Mira,
Yeah.
do you want to answer?
So phase change materials, as we explained earlier, it comes out in the form of a plasterboard, and it can be applied to your walls or ceilings, and it gives you it gives an equivalent thermal mass that of high thermal mass structures, and so that's why we recommend
Is it
that.
thicker? Is it thicker?
It is as thick as a plasterboard, which can be 15 mm thickness roughly. And the
15
15
mm.
mm thickness can give you an equivalent value of the thermal mass that of 100 mm concrete. So which is why it is great. And when we have incorporated them in the dynamic simulations, we have found that the results improve drastically over a period.
Does that help, Peter?
Yeah, I need to learn more about it because haven't heard about it, but it sounds expensive and I don't know how the surface is of that. Is it like plasterboard?
Yeah.
Yes. They are expensive, and so we do make a recommendation to several projects. However, it's the cost constraints that come into play. So we will also refer to the other measures.
Yeah.
However, they can be considered. Also, we need to be careful about, in some situations, there may be fire regulations that interfere with this material. So that should also be taken into consideration when we're considering phase change materials.
Come for lunch, we can teach you more. It's one of these new technologies, they're coming thick and fast, but obviously, you know the pros and cons, but yeah, it's exciting. There's lots of new developments. I think some people have put stuff in the chat.
Yeah, we've got a question from Jamie. What are the suggested G values for each orientation?
I can take that. So generally, as a best practice, we often suggest a G value of 0.4, which is often used in the SRE specifications for the building, because it gives the chance for the SAP assessor as well as the overheating assessor to work together to find a better solution, because 0.4 is like workable in SAP as well as overheating. But in terms of orientations, we can't really specify a specific G value. It would depend on us doing a dynamic simulation and finding out the correct G value for the building. And it has to be noted that when you are having different G values on each facade, there would be a color difference on the glazing, which can be visually not so pleasing. I mean, the architects can understand that. You will be more concerned about it.
Yeah, I
I
think
hope I answered the question.
one of the things that we have learned recently is this contradiction between SAP and overheating. And actually, since we've moved to our office, we have put the SAP assessors and the people who do overheating next to each other in the office, and very often they will be having conversations or looking at each other's models. Sorry, our lights have gone out again. So that they can work together to come up with the best solution for our clients. So yeah, it's interesting. Thank you. Good question.
We've got another one in the chat from Nonzo. What are the effects of these phase change materials on the U value of the wall fabric element, for example?
Thank you, Hazel. That's a really good question. Alicia, do you want to carry on?
Yeah, sure. I can take that. So the phase change material, as we had mentioned earlier, it is similar to a plasterboard, and it is only varying the thermal mass, and it doesn't affect the U value of the structure because it is applied internally, and the U value, it would have a similar impact as a plasterboard has. So I hope I answered the question.
Does that answer the question? Who gave the question? Did you say Onzo?
Nonzo.
Nonzo. Does that answer your question, Nonzo? Yes.
Yes.
Thank you.
Thank you.
Fab, we've got another one. This one's from Prashanta. I have recently completed a building with major overheating. The window spec was not specified with a low G or low E glass. MVHR was removed. Options to remedy this, question mark.
I think.
Sorry, can I just clarify? It's a building that I picked up that was kind of completed during COVID, and it wasn't a building I worked on, but I'm trying to find a way to remedy issues that it's now facing. So it's a extra care property that has severe overheating. I mean, temperatures are soaring during the summer.
Prashanta, this is a really great question. Thank you. I'm aware we've only got 5 minutes, and this is quite a specific question. We've got lots of people on the chat, so what we'll try and do is we'll try and answer it as broadly as possible, and then we'd love to chat to you afterwards. You know, we can give you more specific advice afterwards, because I know we've got lots of more general things. So just answer it quickly, generally, and then we'll give specific.
So to answer the question, since it's a already built development, you can always add on like G value, solar reflective films or films that can be externally applied onto your existing glazing, which can enhance the G value. So we had recently done this in one of our projects where we were struggling with overheating and we were not meeting the required G value, where we just gave the specifications for a film which can achieve a G value of 0.36 or 0.4 to meet the required part of compliance.
Yeah. Does that help, Prashanta?
Thank you. I did investigate that. It removes the warranty from the window company, so I haven't been able to follow that. But I'm happy to take this offline. But thanks very much.
Yeah, that's really good. I think you've got our number, so just give Alicia a call, and we can help you more specifically about that project. Good question. Thank you. The next question.
Yeah, we've got another one here. So this one's from Jonathan Harris. Are there products on the market that integrate renewables with building elements such as cladding or glazing that use/convert the heat energy being kept out of the building?
Are you okay with that, Mira?
Yeah, can I get the question again? Sorry.
Yeah, sure. Are there products on the market that integrate renewables with building elements such as cladding or glazing that use/convert the heat energy being kept out of the building?
Well, I suppose PV panels would be the most obvious one.
I assume here you're meaning about embedding PV panels or into the cladding or the other building elements of doing. There are quite a few products on the market, but I can't specify currently on one specific product, because it needs to, we need to look at the context of the building and have a dynamic simulation done in order to be able to suggest anything on that.
I mean, it's the multi-million-dollar question, and it would be the answer. But I mean, what jumps to mind immediately for me would be solar PV, and I know that they're using quite a lot. Yeah, or solar thermal collectors. Thank you, Richard. I think that would be the most obvious, and I know they're doing that quite a lot on the continent as well. Thank you. What was the next question?
We've got one here from Amy Palmer. Does CLT count as a material that has thermal mass?
Yeah, it depends. I'll take on that question. Thank you. It depends on the composition of it. If your CLT do have elements with thermal mass, of course, yes, definitely. Otherwise, if it's just on either side, insulation and cladding on either side, it can have very less thermal mass. And we have come across these construction specifications where most of the prefabricated structures has very less of thermal mass elements embedded inside. So it really depends on each layer of the CLT. However, generally from whatever we've seen, it always is very less in thermal mass.
Adding on to that, if you can combine the CLT construction with a phase change material on the ceiling, because it has a larger surface area, which will drastically improve the thermal mass of the space. So the impact the CLT has on the heat gains would be counterbalanced by the phase change material on the ceiling.
Any more questions? What strategies, this is from, what strategies can be employed to reconcile the conflict between spatial daylight autonomy and annual sun exposure metrics in facade optimization for thermal, daylight, visual and perceptual performance. Alicia, this is your
Yes.
area.
So generally, the G value does not impact the light transmittance. The internal daylight or daylight autonomy depends upon the visual transmittance value of the glass. So the overheating does not actually interfere with the daylight or the DSO criteria. But yes, the shading, addition of shading, etc. impacts the daylight values. But if you look at the BRE guidance, specifically they mentioned that shading can be considered as like so it's not necessary to account for the shading in your assessments, because shading itself can reduce the internal daylight.
Jubin, does that help you? Does that answer your question? I think, thank you, thumbs up. Any more questions in the last minute or so? We've got none on the chat. Great, can I give you that?
Yeah.
Thank you. So I think we'll bring that to an end. You know where we are. Do pick up the phone and ask us any questions, or if you want further discussions on any of the points that we brought up. Hazel's going to be sending out a link to the recording of today in the next 24 hours, so you can see that on YouTube if you want to watch it again or send it to other people. And also we'd love feedback, so please do let us know if you've got any ideas about how we can make the next CPD better. I know quite a few of you have signed up for all 4 of the CPDs. The last one, we've actually moved the date. It's going to be a week later now, and it's going to be on Thursday, the 6th of June. So at the same time, 1 o'clock. So do make a note of that in your diaries. Thank you and goodbye from all of us.
Bye.
Bye.
Thank you.
Thank you.
Thanks.
Thank you. Thank you.